All right, let's talk about something that happens deep inside the Go compiler, something that makes your code run way faster. We're diving into static single assignment optimization, or SSA for short. And what we're going to do here is build a really solid mental model of what it is, what it does, and why it's so critical for getting great performance out of your Go programs. So you've written your code, you hit compile. What is the compiler really thinking? Well, at this point, it's already checked that your code is valid Go, so it kind of changes hats. It stops being this strict rule enforcer and becomes more of an efficiency expert. And it starts asking itself this one fundamental question over and over: what work in this function is actually necessary? Honestly, that single question is the entire heart of optimization. So here's how we'll break it down. First, we'll talk about that shift in the compiler's mindset. Then we'll get into the real meat of it: dead code elimination and bounce check elimination. We'll touch on a few other cool optimizations, and then we'll wrap it all up by understanding why this all happens at this exact stage in the compilation process. Okay, let's set the scene. We are officially past the early phases. All the syntax errors, all the type checking, that's done. The compiler trusts us, it knows the code is correct. Its job now is totally different. It's all about making that correct code fast. Now, the secret sauce that makes all of this possible is rewriting your code into what's called SSA form. Think about it. Before this, tracking a variable's value can get complicated, right? It can be changed all over the place. But in SSA form, every single value has one and only one origin. It gives the compiler this perfectly clear step-by-step map of your function's logic. And it's this clarity that unlocks all the powerful optimizations we're about to see. When this is maybe the most important rule to remember about this whole process. These optimizations are laser-focused. The compiler is only looking at one function at a time. It doesn't care about the rest of your package, let alone your entire project. Its world, for this moment, is just that one function. It perfects it, and then it moves on. All right, let's look at our first major optimization: dead code elimination. And the name says it all, really. This is all about finding bits of code, computations that happen, that have zero effect on what the function ultimately returns, and just getting rid of them. Now, it's really important to get this distinction right. An unused variable is totally different from an unused computation. You've all seen this, right? You declare a variable, you don't use it, and Go just yells at you. Your code won't even compile. That's a language error. But an unused computation, well, that's different. That's perfectly valid code where you calculate a value, but that result never actually gets used to produce the final output. For the compiler, that's not an error. That is a golden opportunity for optimization. And here's a perfect, simple example. On the left, totally valid Go code. We calculate y, but look at the return statement. We only return x. The value of y has no impact on the outcome whatsoever. The compiler sees this and knows that the entire line y equals x plus 20 is just wasted effort. So after optimization, poof, it's gone. The behavior is exactly the same, but now it's just a little bit faster. Okay, next up is a huge one for Go performance, especially if you do a lot of work with slices and arrays. It's called bounce check elimination. So first off, what even is a bounce check? Well, for safety, every single time you access a slice, like RI, Go secretly adds a little check at runtime. It makes sure that I isn't out of bounds, which prevents all sorts of nasty crashes and security bugs. This is awesome for safety, but those little checks, especially in a tight loop, can add up to a real performance cost. So how does the compiler get rid of it? It's not magic, it's just pure logic. It looks at the code in that super clear SSA form and plays detective. It gathers the facts. Fact 1, it sees a loop that runs from I equals 0 up to, but not including, 10. Fact 2, it sees the slice we're using has a length of exactly 10. It puts those facts together and can mathematically prove with 100% certainty that the indexed I will always be safe. And once it has that proof, it says, okay, this runtime check is just redundant, and it removes it completely. Hey, just a quick note. If you're enjoying these deep dives into how Go works under the hood, you should definitely subscribe to our Gokin channel. We cover advanced topics on Golang internals, architecture, and execution flow that you just won't find anywhere else on YouTube, and it's all completely free. Okay, back to it. The result is pretty straightforward but incredibly powerful. Conceptually, before optimization, you've got the safety check, then the actual memory access. After the compiler works its magic and proves it's safe, you're just left with direct, faster memory access. No more runtime check. And the rule here is just so simple. Safety first. The compiler is conservative. If it can prove without a shadow of a doubt that an index is always safe, it'll remove the check to make your code faster. But if there is any uncertainty, say the index comes from user input, it will absolutely not take that risk. The safety check stays in. And what's really cool is that this isn't some black box. You, the developer, can actually see what the compiler is doing. There's a special compiler flag you can use that will tell you exactly which bounds checks it couldn't get rid of. This is so useful for performance tuning because sometimes you can look at that and realize, oh, if I just rewrite my loop slightly differently, I can help the compiler prove it's safe.
Here, this is like your X-ray machine for bounds checks. Yeah, it looks a little cryptic, I know, but it's an incredibly powerful debug flag you can pass to the Go compiler. It's basically telling the compiler, hey, while you're doing your thing, can you report back to me on one specific optimization, bounds check elimination?
Now, here's the crucial thing to understand. This flag doesn't tell you about its successes. It doesn't tell you what it did remove. It tells you about its failures, what it couldn't remove. So when you see output like this, that's the compiler telling you, hey, on line 11 of main.go, I had to keep a bounds check. I just couldn't prove it was safe. And that is your signal, your cue to go look at that line of code and think, can I rewrite this in a way that gives the compiler the proof it needs? So at the end of the day, it's a diagnostic tool. It turns compiler optimization from this mysterious black box into a feedback loop. It lets you actually partner with the compiler to squeeze every last drop of performance out of your app's most critical. Now, dead code and bounds check elimination are the big ones, but the compiler has a few other tricks up its sleeve during the SSA stage. Nil check elimination works on the exact same principle. Let's say you dereference a pointer. That would panic if it were nil, right? So if the code continues, the compiler now knows that pointer can't be nil. Any future checks on that same pointer in that same code path are now redundant, and the compiler can safely remove them. Devirtualization is a really nice performance win. Normally, calling a method on an interface is a little slow because it has to look up which concrete method to call. But if the compiler can prove that inside a particular function, a specific interface variable always holds the same concrete type, it can just skip that lookup entirely and replace it with a direct, super fast function call. Okay, so far, every optimization we've talked about has been about removing work, but this next one is a little different. This one is actually about adding some very important work. This is called right barrier insertion. It's a bit of a fancy name, but the concept is crucial. For Go's garbage collector to work correctly, it needs to know whenever a pointer gets written to memory on the heap. So during the SSA stage, the compiler analyzes the code and carefully inserts these tiny essential instructions, the right barriers, in exactly the right places to keep the GC informed. So that brings us to the big final question. Why? Why do all of these very specific things happen right here in this particular stage of compilation? And the answer comes right back to the SSA representation itself. It's because SSA gives the compiler this perfect, pristine, local view of the function. It knows the exact control flow, the exact data flow, and exactly how long every single value is alive. It's this complete and total knowledge of one small part of the world that lets it make these big optimization decisions with absolute safety and confidence. So, if you're going to remember just one thing from all of this, let it be this. This is your core mental model. SSA optimizations are all about simplifying and speeding up the logic inside a single function. And it's all made possible by that super clear SSA representation. And just to hammer that point home one last time, this whole process is local, local, local. All the global stuff, like linking your whole program together into one executable, that happens much later, in totally separate stages. And that leaves us with one final, thought-provoking question. Now that you have this mental model, now that you can see the logic the compiler uses, how might that change the way you write code? How can you structure your loops or handle your variables in a way that makes it even easier for the compiler to do its job and make your code fly?